Okay, let's begin with separable equations. A separable differential equation is the simplest form of differential equation to solve. They have a special feature that make them easy and make them approachable. And that special feature is that the right-hand side of the differential equation have separate into some function of x multiplied by some function of y. That is why we name it separable. So let's take a look at the definition. So a separable equation is a first order differential equation that can be written in the form dy by dx equal to gx times fy. As I said before, you can see that the x and the y have separate on the right hand side. For example, if I have a differential equation dy by dx equal to 3x squared sine x multiply y squared plus 2y. This is called separable equation because on the right hand side you're gonna see a function of x multiplied by a function of y. But if I have a differential equation dy by dx equal to x plus y, even though this is simple, but this is not separable because on the right hand side you don't have a product of a function of x times a function of y. Does it make sense? Well, in order to solve a separable equation, you just need to move everything that depends on x into one side and then move anything that depends on y to another side, and then after that you integrate on both sides. That's all. That is how we solve separable equations. Let's take a look at some examples. So example number 2, solve the following differential equations. So we have two parts. So let's do part A first. So part A, the differential equation is dy by dx equal to 6x squared over 2y plus cosine y. You can see that this is a separable equation because on the right hand side, actually I do have 6x squared multiplied by 1 over 2y plus cosine y. So actually this is a separable equation because you have a function of x multiplied by a function of y, right? So this is a separable equations. So x and y, they stay separately. So the idea of solving a separable differential equations, you can move everything in terms of x into one side and move everything in terms of y to another side. So what I'm gonna do is, I'm gonna simplify it. So I get 2y plus cosine y multiply dy equal to 6x squared multiply dx, and then after that you integrate on both sides, so you get integrate 2y plus cosine y dy, and then equal to integrate 6x squared dx, and then now you can just use the integration technique that you have from calculus 1. So integrate 2y, so you get 2y squared over 2, and then integrate cosine, you get sine, and then integrate 6x squared, you get 6x cubed over 3, and then plus c. Simplify a little bit, so you get y squared plus sine y equal to 2x cubed plus 3 plus c. And this is your general solution for this differential equations. This general solution, you can see that it is in the implicit form. This is implicit form. What I mean by implicit form is just you cannot simplify until you get y equal to something in terms of x. If you can get y equal to something in terms of x, that thing is called explicit form, right? Sometimes you just cannot get explicit form because the explicit form is not easy enough to write it. So here on the left hand side you have y squared plus sine y, so you just stop there, and that's all we want, because if you solve for y equal to something, it's gonna be messy. Now let's take a look at part B. So part B, we have y prime equal to y times x squared plus 1, where y is positive. So the the differential equation is separable because on the right hand side you can see the product of y and x squared plus 1. So we're gonna start by doing the same thing with question in the part A. So we're gonna separate y on one side and then separate x to another side, and then we just integrate on both sides. So to make it easy, I'm gonna switch y prime to the notation dy by dx. So this question I will have dy by dx equal to y times x squared plus 1, and then I move y to the left hand side, so I get 1 over y dy, and then I move x to the right hand side, so I get x squared plus 1 times dx, and then after that I integrate on both sides, so integrate 1 over y dy, I get log absolute y, and then integrate x squared plus 1 dx, I get x cubed over 3 plus x. And then after that, I simplify a little bit, so I get absolute y equal to e, plus c here too as well, sorry. And then I get e raised to the x cubed over 3 plus x plus c, right? And then because y is always positive, so the absolute doesn't matter, so I have y here on the left hand side. On the right hand side, if I simplify a little bit, so I can pull out e to the c, right? And then because this is constant, so now I get e to the c times e to the x cubed over 3 plus x, right? And that e to the c is just another constant, so I can say this is y equal to c1 e to the x cubed over 3 plus x, right? Because e to the c is just constant, so I can rename it as a c1, and that's all. That is my answer for this question. So a general solution for this differential equation is y equal to c1 times e to the x cubed over 3 plus x. So this question actually you can solve y equal to something in terms of x. This is called explicit form. If possible, if you can solve for an explicit form, well, you should. Alright, let's move to example 3. Alright, let's move to example number 3. Show that the general solution of the first order linear differential equation y prime t equal to ky plus b, where k and b are specified real number, is y equal to c times e to the kt minus b over k, where c is an arbitrary constant. So let's take a look at differential equations. So the independent variable here is t, not x. So from the equation y prime t equal to ky plus b, I can rewrite it as dy by dt equal to ky plus b, right? And then on the right hand side of this differential equation, you can see that it is separable because it is a ky plus b, which is a function of y, multiply 1, which is a function of t. So actually this is a separable equation. So in order to solve this thing, I'm going to move everything in terms of y to the left hand side and move everything in terms of t to the right hand side. So what I'm going to get is I'm going to get dy over ky plus b equal to dt. And then after that, you integrate on both sides. So in order to integrate 1 over ky plus b dy, so I'm going to just do this. So this is 1 over ky plus b. And then I switch dy to dky plus b. And then I need to have constant k here. And then equal to dt. And then here I have integrate 1 over u du. So this is easy. So I get 1 over k times logarithm of ky plus b equal to t plus a constancy, right? And then after that, I have logarithm of absolute ky plus b equal to k times t plus constancy. And then after that, I have absolute ky plus b equal to e to the k times t plus c. Alright, now we're gonna assume that Okay, let's make this line first. So now we're gonna assume that ky plus b greater than 0, so you don't have to worry about absolute value. So I have ky plus b equal to e to the k times t plus c. Alright, and then after that, so I can simplify on the right hand side, so I get e to the kt plus no, not plus, multiply e to the k time constant c. And then after that, I get ky equal to e to the kt times e to the kc minus b, right? And then divided everything by k, so I get y equal to e to the kt times e to the kc minus b over k, right? Well, the goal is we're trying to simplify until we get the given term here, the given solution here. So it looks similar now. I just need to change all my constant here. So I have the constant that I circle here, e to the kc over k. So I change it to another constant c. And that is the answer. So I get y equal to c times e to the kt minus b over k. This is my general solution. And we prove it. So if you want to be more clear on that constant, this is just the constant. So you can change the constant c at the first to be c1. Change everything to c1 here, so it is going to be your different notation, and then that c equal e to the kc1 over k. Alright, let's move to example 4. Solve the following initial value problem dy by dx equal to e to the x minus y, where y of log 2 equal to log 3. So this is the initial value problem because we have the initial condition here. So let's start by solving for a general solution first. So we have dy by dx equal to e to the x minus y. You can separate it to e to the x times e to the minus y. And then we're going to move e to the minus y to left hand side. So I get 1 over e to the minus y dy equal to e to the x dx. And then after that, I have e to the y dy equal to e to the x dx. And then I integrate on both sides. So I get e to the y equal to e to the x plus c. And if I simplify a little bit, so I get y equal to log e to the x plus c. This is our general solution. General solution. But to solve the initial value problems, you have initial condition here. So we're going to use the initial condition to solve for a constant c. So the initial condition y log 2 equal to log 3 means when x equal to log 2, y equal to log 3. So that means if I replace x by log 2, I'm going to get y equal to log 3. So that means log 3 equal to log of e to the log 2 plus c. You can start from here and then use it to find a constant c. So here I'm gonna get log 3 equal to log e square. Oh no, sorry. E to the log 2 is 2. Log 2 plus c. And then after that, well, if I cancel log on both sides, so I get 3 equal to 2 plus c. And c is equal to 1 at the end. After you get c equal to 1, so you can plug in c equal to 1 into the general solution, and that will give you the solution of the initial value problems. So to sum up, the solution of this initial value problem is y equal to log e to the x plus 1, right? Because you just plug in 0 to 1, and that's all.